and how to determine the direction of these currents. What you read in your textbook is the induced current in a loop is in the direction that creates a magnetic field that opposes the change in the magnetic flux through the area enclosed by the loop. It's a long sentence. Probably it means not much of things to you, but let's think about in just pictures. So it says that if you have like this moving bar in a loop circuit, in a rectangular loop, and if you move the bar in this direction, the velocity is to the right, right? And if you move this bar to right at a constant speed, of course, because of the change in the flux, but the change of the flux is through this rectangle formed by these rails, this resistor, and this lower rail, and the bar. So when you move, think about this. When you move this bar, green bar, toward right, is the flux increasing or decreasing? The flux is increasing, right? And that means the flux is changing over time. That means if the flux is changing, there is an electromotive force. There is a battery provided by the bar. And if there is a battery, and this makes a closed circuit, and there will be induced current because of this electromotive force. And what about the direction of the induced current? The induced current is in a direction such that if the flux is increasing when the bar is moving toward right, the induced current will produce its own flux through this loop, rectangular loop, so that it will try to decrease the flux. Okay? That means always the induced currents will produce fluxes that opposes the change of the flux because of the motion of the bar. So the motion of the bar is such that it is increasing the flux, and the direction of the current induced by this change of flux is such that it will decrease the flux. Okay? So there is only one way, of course, to decrease this flux. It must produce a magnetic field which is in opposite direction to into the page magnetic field. So the magnetic field provided by this current will be in such a way that the magnetic field, it is produced by the magnetic field by this current, will be out of the page because it must oppose to the increasing flux through the loop. So there is only one way to produce a magnetic field through this rectangular region which is out of the page, is this direction. So the current must flow counterclockwise, right? So this the last law is about the direction of the currents. To determine the direction of the currents induced by the change of flux provided by the motion of the bar. Okay, so what can you tell about the second picture? Well, I think I already given the direction of the current. So if you move the bar instead of right to the left, like in this picture, then the induced current will be in the opposite direction, of course, because this time you're decreasing the flux by moving the bar. You're decreasing the flux through this changing rectangle. Decreasing the flux will mean that the induced current will produce its own magnetic field so that it will increase the flux. And this is there is only one possible way to to do this, that the current must flow in the clockwise direction. If it moves in the clockwise direction, then it will oppose the change of the flux provided by the motion of this bar. Okay, think about this picture. You move a bar magnet, which has the polarities south and north to the right and the south to the left, toward a ring, a metal ring. This metal ring, if you move the bar toward right with this velocity, will produce a current that flows in this direction. Why? What happens if I move the bar toward the ring? Will the magnetic flux increase or decrease through the ring?
Increase.
It will increase because the portion of the bar that has the higher intensity of lines will come close to the ring. That means it will increase the intensity of the magnetic field. If the intensity of the magnetic field is increasing, then the flux will increase. So it will produce a current in such a way that this current will produce a magnetic field that will decrease the flux. If you put your forefingers like this, it will produce a magnetic field which is in this direction, and it will opposing the increasing magnetic field lines through the ring. Okay. If you move in the opposite direction, if you move the bar magnet in the opposite direction without changing its polarities, then in that case, the current induced by this change of flux will be in the opposite direction. Right? The flux is decreasing now. It will produce a magnetic field so that it will be in the magnetic field will be in this direction. In this direction, from left to right, to keep the flux constant or increasing. Because if you move the bar toward left, you're decreasing the flux. And the current will try to increase the flux, so it must produce the magnetic field direction which is the same direction with that of this north pole. Because it will try to increase the flux. So that means this current will produce a magnetic field which is in the same direction with the magnet, but in here it will produce a magnetic field which is in the opposite direction with the magnet. Okay? Any questions? I have an example. There are 4 different configurations. You see, I think this is easily seen from distance. So you have the first one, you have a resistor, a rectangular circuit, and it is circulated through a cylinder, right? And this core of the cylinder is a metal object, and it is a ferromagnetic object, okay? That means it will allow the magnetic field lines go through this solenoid. So you have on this end a bar magnet. North pole is this end and the south pole is this end. It moves toward left with some certain velocity. So in the second picture you have a battery, and the battery, this part has the plus polarity and this side is minus polarity, and you have a switch, and you may close or open the switch, and you have a second loop going through this cylindrical ferromagnetic cylinder, and you have a resistance here. In the third picture, C, you have a current carrying wire, and the current flows toward left, and from a distance you keep a rectangular loop which has a resistance R. And lastly you have a bar. The bar is moving toward right. I think it's moving toward right inside a magnetic field, so that you have a plus polarity and minus polarity. I don't know. We will read from the question. And can you read the question? Okay, the first question is, using the Lenz's law, part A, what is the direction of the induced current in resistance R in part A when the bar magnet is moved to the left? So what happens to the flux through this loop when you move the bar magnet toward left? It is decreasing, yes. If it is decreasing, then the induced current must produce a magnetic field which is a magnetic field direction which must be in the left direction or right direction. The flux is decreasing. If the flux is decreasing, so it must be toward the magnetic field produced by the current on the resistance R must be in the direction of left or right. Why left? Okay, so what happens with this configuration at any constant instant of time, the magnetic field through this core is toward left, right? Because, sorry, it is toward right. Okay. The magnetic field at any instant of time through this core is toward right. Right? Because field lines always emerging from the north pole and comes to the south pole. But if you move the magnet toward left, you are decreasing the magnetic field, which is in this direction. You are decreasing the magnetic field, and you are decreasing the flux, which is in this direction. And the current must induce a magnetic field that keeps the flux increasing in this direction, right? So the current will be magnetic field in this direction, and the current is going like this. So the current will go in this direction, right? The current through the loop is in the counterclockwise direction. You have to be careful in here, okay? Because the Lenz's law looks simple, but you must be careful anyway. So next question is, okay, you have any questions with the first one? Next question is, what is the direction of the current induced in the resistor R immediately after closing the switch S in part B, in this part? So you have two loops. One is this one, and the other is this one. If you close the switch, what happens? In which direction? When you close the switch, initially there is no magnetic flux, right? When you close the switch, the current will flow in the clockwise direction in the first loop, right? The current will flow in this direction. So it will increase the flux toward left, right? And there will be induced current in the second loop such that the magnetic field created by this current must be in right. And that means the current will flow in this direction. Go this. Right? Any questions on the second part? I think this is also understood. Part C. Evet, kendi aramızda şey yapmayalım arkadaşlar. Var mı bir sorunuz? Part C, what is the direction of the induced current in R, the resistor, when the current I in this cable decreases rapidly to zero? So you have this current in the cable, but this current toward left is decreasing. Okay? And what happens to the direction of the current which is induced on the loop here, on the rectangular loop? What is the direction of the magnetic field through this current loop, rectangular current loop? Into the page. Good. By right hand. Into the page. And the flux is into the page. But if the current in the cable is decreasing, then what happens to this flux? The flux is decreasing. So if the flux is decreasing, then the induced current will try to increase the flux. And to increase the flux, it must produce a magnetic field which is into or out of the page? Into the page, because the flux is decreasing. Right? So what is the direction of the current then? Through the resistance R. It must be in the clockwise direction, yes. Because it must produce, the current must produce magnetic field which is into the page, because the magnetic field into the page is decreasing. It must increase this. So into the page, then you just point your thumb into the page, and this direction of the four fingers is the clockwise direction. Any questions about the third one? What happens if the current is increasing through the cable? It must be on the counterclockwise. If the current is increasing, then the flux through the loop is increasing, and the induced current must decrease this flux. So the last one. A copper bar is moved to the right while its axis is maintained in a direction perpendicular to a magnetic field as shown in the figure. If the top of the bar becomes positive relative to the bottom, what is the direction of the magnetic field? So you move a metal bar toward right with this, and you just realize that the upper part has a positive polarity and the lower part has negative. What is the direction of the magnetic field in this region? Into or out? How do you determine this? You move this bar, metal bar, toward right with this, and you realize that the upper part has positive polarity and the lower part has negative polarity. So, into. How do you find this, whether it's into or out? What the right hand says about the charges and moving in the magnetic field? What is the expression for the magnetic force on a charge Q which moves with a velocity v inside a magnetic field B? Formula. Q times V cross B, cross product. V cross B. V, let's V, okay, let V cross B. If the magnetic field is into the page and your palm is facing like this, you rotate like this, and the thumb shows the direction of the force on the positive charges. So this is the case in here.